Hello all, welcome to the next class. So, we have been very successful at constructing our first realistic phase diagram. We have actually derived the phase diagram of water just from classic Clausius-Clapeyron equation, which actually so we interpreted the Clausius-Clapeyron equation as so how on the P versus T phase diagram am I going to move from one point of equilibrium to another point of equilibrium. And we knew some of these points of equilibrium in water, right. So, 1 atmosphere 0 degrees Celsius is my melting point. If I am looking at solid to liquid phase transition, 1 atmosphere 100 degrees Celsius is my boiling point if I am looking at liquid to vapor phase transition and so on. And based on this so we were able to get some nice analytical functions that describe that phase equilibrium, right. So, of two phases, right. And then wherever these two phases met, we said alright. So, that is where you have a 3 phase equilibrium, and this is what is called the triple point, right. And then we said, look, if my water or if H2O exists anywhere here, right. So, the only phase that thermodynamics says is possible is the vapor phase, or the most stable phase is the vapor phase. If it exists anywhere here in these pressure and temperature points, the only phase that exists should be the liquid phase, right. So, and here similarly it should be the solid phase. If it exists anywhere on this line, then I have a solid liquid phase equilibrium. If it exists anywhere on this line, then I have a liquid gas solid gas phase equilibrium and so on, right. Now, alright, that is fine, but also so it also tells me something about the kinetics, that alright. So, I can take a vapor or I can take a liquid and suddenly reduce the temperature to a very low temperature, and then I have a driving force, right. So, given by this sort of an undercooling that will tell me how much is so when will my solid form, right. So, I can estimate driving forces, I can estimate so given how far away I am from the phase equilibrium lines, right. So, I can get an estimate of what the driving forces are for the new phases to form from the old phases, right. So, the phase diagram tells us a lot of things, okay. So, we will keep on looking at phase diagrams, okay. Now, just to give you one more case study, so one more realistic scenario of where I can use the water phase diagram, right. So, so let us look at the idea of what is called boiling. What is boiling? Boiling is, or boiling point, I have defined boiling point to be 100 degrees Celsius at 1 atmosphere. So, the question is so liquid converts to vapor, so at 1 atmosphere at 100 degrees Celsius, okay. So, I have a liquid or I have water, and this water would convert to vapor, I am saying at the boiling point, right. But it is your everyday experience for people who actually dry clothes, right. It is your everyday experience that you do not need to really heat your clothes up to 100 degrees Celsius. So, you wash clothes, you dry them in sun, right. So, by evening I put them in the afternoon, and especially so currently I am teaching you in summer, right. So, in Bangalore this is summer right now, and in summer it is much faster for the water to just evaporate, and so the water goes away and then my clothes are dried. But I have changed water from liquid to vapor phase, but I have not really heated the temperatures are hot, they are 32 degrees Celsius or 33 degrees Celsius, but it is not 100 degrees Celsius outside, right. So, I am not boiling water, and the atmospheric pressure is still 1 atmosphere, right. So, I am not boiling water, but somehow water seems to be still going away and I am able to dry my clothes, right. So, can I explain that, right. So, first using I will be able to explain that using the phase diagrams, right. So, and then from there we will look at what really boiling is, right. So, so what is boiling of water compared to what is just a normal drying or normal evaporation. Okay. Now, so I am hanging clothes, this is a cloth hanger, right. I have fixed it to something in my balcony or something in my terrace, and I started hanging clothes. This is cloth 1, this is cloth 2, this is cloth 3, and so on and so forth. Okay. So, essentially all these cloths have some water on it, right. So, because I washed it with water. Okay. Now, let us say, so this is water. This is water on the surface of my cloth, right. So, let me look at the water phase diagram, right. So, at the so the water phase diagram is pressure versus temperature, right. So, I have this is solid, this is liquid. So, what I am more interested is in liquid versus gas phase diagrams, right. So, okay. Let me just draw it properly. So, this is solid, this is liquid, this and this, right. So, this is liquid, this is gas. Okay. So, I want to go from liquid to gas. Okay. This is the transformation I want to do. Okay. So, this is at so let us say the atmospheric pressure or the temperature at which I put my cloth is 32 degrees Celsius. Like I said, today's temperature in Bangalore is 32 degrees Celsius, and at 32 degrees Celsius my phase diagram tells me that so this is, let us say, 32 degrees Celsius, and this is 1 atmosphere. I am at 1 atmosphere, and this is 32 degrees Celsius. At 32 degrees Celsius, my phase diagram tells me that I have a liquid phase that is stable. Okay, that is fine, that even I know, right. So, even my grandmother knows that, right. So, at 32 degrees Celsius, liquid phase or water is the stable phase. All right. What does it mean that water is a stable phase? So, water is a stable phase means, if I have a container of liquid like this, or a cloth with, this is the cloth, but then the cloth has all these water droplets, right. So, it is soaked in water, right. So, it has a film of water on the top and film of water on the bottom, right. So, if I look at the depth of this, right. So, here of course, water is a stable phase. Okay. So, all these molecules are nicely sitting in one phase, and that is the water phase, or that is the liquid phase. Okay. Now, what about my molecules? So, inside this container they are all fine. Okay. So, what about my molecules on the surface? On the surface I have some criminals, right. So, they are not going to follow the rules of what is happening inside the bulk, right. So, these are the rule breakers. They are like, all right, so I am on the surface, I do not really need to belong to water, the phase that is water, right. So, I am on the surface, and what is this surface? This surface is dividing my liquid water from the gaseous atmosphere, and this gaseous atmosphere also has water vapor in it, right. So, some pressure is contributed by water vapor, right. The atmosphere consists of water vapor, right, trace amounts of water vapor, but mostly oxygen, nitrogen, right, and other gases, but I have some partial pressure of water vapor in the atmosphere. Okay. So, there is some pressure of water vapor in the atmosphere. So, what does it mean that my surface molecules, right. So, they are free now, they can either by virtue of them being at the surface, they can either belong to the water phase or they can either belong to the gaseous phase, right. So, they can be water in the liquid phase, which is the bulk of the water, the bulk of the container, or bulk of the film on the cloth, right. So, the water film on the cloth is in water phase, but the surface molecules, right. So, they can they are either in water phase or in vapor phase, right. So, they can just go up, come down, go up, come down, right. So, they can degas, they can sort of go away into the vapor phase, come back into the water phase, and so on, right. So surface, right. So if I am looking at it on the surface, the same water which is in a liquid phase inside exists in a water to water and vapor, water vapor equilibrium, right. On the surface it is like, you know, so I am driving on the border, right. So, you know, let us say I like driving, and there is this is you know, let me try to draw Karnataka, this is Karnataka, right, and somewhere here comes Tamil Nadu, right. I am driving somewhere here on the border, right. So I can be in Karnataka, I can be in Tamil Nadu, I can be in Karnataka, I can be in Tamil Nadu. So this is Karnataka, this is Tamil Nadu, and then, you know, this is Andhra. Okay. So when I am driving on the border, I can either be in this state or this state or this state or this state. So I am sort of, I am not bound by rules of staying in one state, right. So I am here, I am there, I am here, I am there. So as I am this free spirited person who is either here or there, right. So like that, my surface molecules, they are rule breakers, they do not belong to one phase, they are both in the vapor phase and in the solid phase, and in the liquid phase, right. So they can exist between both of them, right. So just the surface molecules, inside fine, I am in a water phase, right. But the surface is always the culprit, right. So surface molecules can be either here or there, okay. Now then I ask you the question, so what is this equilibrium that you are really talking about for the surface molecules, right. Now the surface molecules also happen to be, you know, so this is the liquid vapor equilibrium, right. The surface molecules also happen to be at 32 degrees Celsius, correct, right. So then the question is, you know, so in the vapor phase, right, so they are at 32 degrees Celsius, right, but in the vapor phase, right, what is the pressure of water vapor, right. So I mean, water vapor, you talk about pressure of water vapor, right. So not really, so the water is under some atmospheric pressure of 1 atmosphere, right. The total atmospheric pressure is 1 atmosphere. So in the bulk, fine, I am still in a liquid phase, right. But on the surface, right, so there water can exist either in outside or either inside, right. So it is in an equilibrium state, right. So what is the pressure of the water vapor on the surface, right. So it can exist either in water vapor phase or in liquid phase, right. So Pi, when it exists in a water vapor phase, there is always some constant pressure, right. So that is built up on the surface, and that pressure is that of the water vapor pressure, right. So Pi on surface, right, or the saturation pressure, what is called the saturation pressure, and that, so at 32 degrees Celsius there is one particular Pi sat that determines what is the equilibrium at which my vapor is in equilibrium with the water, right. So and at surface you assume that equilibrium sort of exists, right. So Pi sat is where the vapor on the surface, just on the surface, right. So let us not go deep outside the surface on either side, right. So let us just be on the surface, right. So where the vapor on the surface is in equilibrium with the water on the surface. So then the partial pressure of water vapor on the surface, or what is called the saturation pressure, that is given by the phase diagram, and that is nothing but Pi sat, I for partial pressure of water vapor and sat for saturation, okay. So let us remember this number, okay. On a less, let us say, humid day, right, atmosphere itself, right. So where is atmosphere now? This is bulk of water and this is bulk of atmosphere. Atmosphere has some partial pressure of water vapor, right. Right, so atmosphere also has some partial pressure of water vapor, okay. Let us call that as Pi, So, very simply the partial pressure of water vapor here should be P sat, where the liquid droplet is in equilibrium with a water vapor. So, they are nice and they are in good equilibrium here, whereas somewhere far away the atmosphere has a water vapor pressure of Pi, right. So, this is the Pi, which is the water vapor pressure of the atmosphere. Okay. Now, this Pi divided by Pi sat, this is called the relative humidity, right. So, if humidity is low, means Pi is very low, it is a very dry conditions, which means I do not have so much water vapor in my atmosphere, right. So, the water vapor pressure can keep changing in the atmosphere, right. So, you look at weather channel today and then say that, oh, it is a very dry day, So, a dry day means there is not much pressure of water vapor in the atmosphere, right. So, the Pi is very less, okay. But if it is a very humid day, you are sweating, that means that so the atmospheric water vapor is coming and condensing on you, there is huge amount of atmospheric pressure, atmospheric water vapor pressure, right. So, this Pi by Pi sat is what is called relative humidity, and when relative humidity actually increases beyond 1, that is when it rains, right. So, that means that the pressure, the saturation pressure, right. So, now there is no liquid or anything, but the saturation pressure at that temperature is given by Pi sat, that is given by my phase diagram again, right. If Pi is greater than Pi sat, then so then I try to come back to a liquid phase, right. So, I cannot be in a solid in a gas phase, right. So, I try to condense, right. So, I have condensation, or I have rainfall and things like that, right. So, this is well known, right. Now, here I am assuming I have a dry day, so that I have put my clothes. So, on a dry day Pi is less than Pi sat, right, and Pi sat is the pressure on the top of my cloth, right. So, on the top of the film, of the water film on my cloth, right, and Pi is somewhere else, right. So, so water vapor tries to go from a region of higher pressure to a region of lower pressure, right. So, so whatever so this is my cloth, this is the film on the cloth, this is the water film. So, here the vapor pressure is Pi sat, here the vapor pressure is Pi. So, when this liquid turns to vapor, it just convects outside, right. So, it just goes away, right, because water vapor tries to go from a region of low pressure to a region of high pressure. I have convection and that is it, right. So, this is gone, the first layer is gone. Then the second layer gets exposed as surface, the second layer is gone, third layer is gone, fourth layer is gone, and so on and so forth, right. So, as long as I have a dry day, or Pi is less than Pi sat, right. In fact, my Pi sat minus Pi tells me the driving force for drying to occur. If Pi sat is much larger than Pi, then it will dry very fast. But if Pi sat is just larger than Pi, then it will take long time, right. Okay. So, that is how you dry clothes. Okay. Now, how can I increase the driving force to dry clothes? So, again this is based on our everyday experience, right. So, okay, so this one and this one, right. So, this is liquid, this is vapor, right. So, I am at 32 degrees Celsius, this is Pi sat, right. Now, Pi sat at 32 degrees Celsius is less than Pi sat at 45 degrees Celsius, right. So, that is what this curve is saying. So, at 45 degrees Celsius the Pi sat is even lower, right. So, even larger, right. So, on a hot day my Pi sat minus Pi, right, Pi sat is larger, correct. So, on a hot day I dry my clothes faster. So, on a hotter day clothes dry faster, right. On a humid day where this Pi is large, right, so the clothes do not dry, right. So, I need a combination of hot and dry, right. So, I can dry my clothes under hot and dry conditions. Dry means less relative humidity, hot means larger temperatures. these are ideal for drying. Okay. So, so just a simple phase diagram explains me how I am drying my clothes, right. So, the drying however happens because of surface water, and the surface water is always under equilibrium with in both in vapor phase as well as in water phase. It imposes some vapor pressure, right. So, that vapor pressure is the equilibrium vapor pressure, right. And at surface the water and vapor are in equilibrium. So, there is always some equilibrium vapor pressure that develops at the surface, right. And if this equilibrium vapor pressure that develops at the surface is much larger than the pressure which is in the atmosphere, then this water just goes away in the vapor phase, right. So, once the water just goes away in the vapor phase, the film thickness is reducing, the film of water on your cloth, right, that you have washed it, that is reducing, right. Then the next layer gets exposed, that also now again there is a surface equilibrium coming up, right, and there is a convection, right. So, after surface equilibrium, after Pi sat is much greater than Pi, so this water is also evaporating, right. So, this process of nicely evaporating the surface molecules one after the other, right. So, process of nicely evaporating right, that is a simple idea of what is called evaporation, right. Evaporation always happens from the surface, right, or drying in this case, right. So, in this case it is drying of clothes, but in general that is the nice evaporative process where so you are nicely evaporating the surface molecules one after the other, okay. Now, let us do something, right. So, all right, so P versus T. Again let me draw this, and this is solid, this is liquid, this is gas, okay. So, I am at Celsius, this is let us say 1 atmosphere, and that is 100 degrees Celsius, okay. Now, let us say now I take a container, okay. So, clothes drying is fine, right. So, I do not dry clothes, so that is why I do not need to dry clothes at 100 degrees Celsius. I can still dry it at lower temperatures, but my surface molecules get into this equilibrium with the vapor phase and they take care of my drying, okay. Now, in a container also the same thing happens, surface molecules keep on evaporating, that is how so I can put a small amount of water on in hot conditions and I can come after 3-4 days and I will see that the entire water has just evaporated, okay. So, that I can do, right. But let us say I am heating this water to 100 degrees Celsius, or okay. So, let us say so initially I have heated the water to about the room temperature is some 30 degrees Celsius, but from room temperature I have heated this water, right. So, on a gas stove, let us say I have heated this to about 60 degrees Celsius. Now, I said that the surface molecules are evaporating, that is okay. Okay, surface is fine, I understand. What happens to the bulk? Okay. So, I said bulk is in a water state, water phase, or water meaning liquid phase, okay. Okay, why? That is the question, right. So, what happens if there is some gas bubble in the bulk, right. So, let me just, for argument's sake, let me create a gas bubble. In bulk, and this is at what temperature? At some 60 degrees Celsius, right. All right. So, at 60 degrees Celsius I have created a gas bubble in the bulk, right, and that gas bubble since the idea is, let us say that the gas bubble exists in equilibrium with the surrounding. So, that gas bubble should have a pressure defined by this, right. So, this is the pressure of the gas bubble, P gas bubble, right. Now, what is the external pressure that is being applied on this gas bubble? This gas bubble has a pressure of P gas bubble, right. At P gas bubble, it will be nicely in equilibrium with the surrounding, right. But externally, I am already applying a pressure of 1 atmosphere, and 1 atmosphere is larger than P gas bubble, right. So, when I am actually applying a larger pressure on this gas bubble, I am just going to burst the gas bubble, right. So, the gas bubble bursts, right. So, there is a larger external pressure than the pressure of the gas bubble. At 60 degrees Celsius, right. So, these gas bubbles are unstable, even if they are created they just burst, right. So, at 60 degrees Celsius I do not have gas bubbles in the bulk. So, at 60 degrees Celsius gas bubbles in the bulk are unstable. So, they do not have any stability, even if they form by mistake they will just die. Okay. So, even if they form by mistake they will die, okay. And here the constraint is 1 atmosphere, which is the external pressure, is greater than my P of gas bubble, dictated by thermodynamic equilibrium, okay, from the thermodynamic phase diagram, okay. Now, at 101 degrees Celsius what happens, right. So, I mean, or greater than 100, right. So, 100 plus delta, right, slightly larger than 100, okay. Then so again going back to my phase diagram, all right, this is liquid, this is gas, and this is 1 atmosphere, this is 100 degrees Celsius, right. So, I am slightly above this, which means I am at 101 degrees Celsius. So, the P of gas, this is the P gas, gas bubble now is greater than 1 atmosphere or slightly greater than 1 atmosphere, okay. Then what happens is, once I have so I have all this liquid and I have some bubble formed. Now, this bubble is no longer being squished by the 1 atmosphere, right. So, there is a 1 atmosphere, but then this is 1 atmosphere, right. So, this is under 1 atmosphere, but this is no longer this pressure of the bubble is larger than 1 atmosphere, right. So, the pressure wherever this bubble is larger than 1 atmosphere. So, this bubble then goes out, it vigorously boils and comes out, right. So, goes out to regions of lower pressures, the outside atmosphere is at 1 atmospheric pressure, right. So, then gas bubbles nucleate, this is the nucleation of gas bubbles. They nucleate, but they are not squished, they are stable, right, and then they come out of the liquid, right, and it shows some vigorous bubbling, right. So, in this vigorous bubbling, this nucleus is a very stable thing, once it forms it just expands and then comes out, right. So, in the form of a water vapor, right. So, then the entire bulk of liquid starts converting to gas, right. Now, this is the idea of boiling, this vigorous bubbling that happens when the pressure in the gas bubble that is created in the bulk is larger than 1 atmosphere, that is when it will just come out, right. So, it will vigorously bubble, and that is the idea of boiling, and it is different from the idea of evaporation, right. Now, boiling is a phase transition, complete bulk phase transition, whereas evaporation is a surface phenomenon. Right? It is still a phase transition, but happening at the surface. Okay. So that's the difference between boiling and bulk and evaporation, right. So boiling, you have to vigorously bubble out, and bubbling out from the bulk, right. So that is, and so in explaining this, I have also explained you what nucleation is. Once this bubble is formed, this bubble should be stable, and this bubble should be able to grow, right. So bubble is formed, bubble is stable, what is called the nucleus, and now this nucleus has enough driving force to grow. Okay. So that is delta G. Now here is given as so P of the bubble minus 1 atmosphere, right. So that is your delta G, right. So once it has enough driving force to grow, it will grow and then just consume the entire, then it will consume the entire liquid, right. So bubbling is a boiling is a very vigorous phenomenon, right. So by boiling, the entire liquid just undergoes a phase transition. In the bulk, it is a bulk phase transition, whereas evaporation is a nice surface evaporation phenomenon or surface drying phenomenon, and so eventually, because of finite volume of your film, of your water, the entire thing dries away, right. But if you have infinite volume, the entire thing is not going to dry away, right. So it depends on so the how much water you remove depends on so how much water you have to start with, okay. But boiling is not like that. Beyond boiling, there is no way, no bulk, no surface, everything should be gas, okay. So that is the idea of boiling versus the idea of vaporization, okay. So all right, again, so so these phase diagrams help you understand your day to day things, right. So here is a very simple example of drying and boiling, right. And through boiling, remember this bubbling, the formation of bubbles inside the bulk and their growth. If I find conducive conditions for that, that is when I find conducive conditions for phase transition, and here the phase transition is bulk water transforms into bulk gas or bulk vapor, right. And how did I find that conducive condition? I have formed a bubble, and the pressure near that bubble is larger than 1 atmosphere. So the 1 atmosphere cannot just come and squish my bubble anymore, right. At 60 degrees, however, I can randomly form these bubbles. This is exactly how I am going to discuss the nucleation theory later on, right. So I can randomly form bubbles in conditions where the new phase is not conducive to form, but I can have some statistical fluctuations where these bubbles are formed. But as soon as they are formed, they are squished, because the outside atmosphere is larger, right. So these are unstable bubbles, they just die down, okay. So that is why I was telling you that just understanding water gives us a lot of insights into phase transitions, and so boiling is a phase transition, evaporation is nice surface phenomenon, right. So it's a you are still drying your clothes by evaporation, but you are vigorously changing the phase of water to gas by boiling it, okay. So that is the difference. All right. So with that, we will again meet in the next class, and in the next class we will try to look at more into the phase diagrams by changing the N1s and N2s, okay. That is the species, right. So we will go into a real open system and try to see how these phase diagrams can be constructed. All right. Thank you very much.